Here we define a new parameter c. C is sine phi divided by square root of 2 refractive index difference delta. And as we know, for guided modes, to successfully induce the TIR, we must have sine phi smaller or equal than square root of 2 refractive index difference delta. According to this condition, we know that for guided mode, the value of C should be between 0 and 1. Okay, so for guided mode, the C value should be between 0 and 1. And then let us rewrite the phase matching condition. For the phase matching condition for guided mode, we know that it will be as the following equation. According to the definition of C, we take the definition of C into here, we can rewrite the phase matching condition in this way. And of course, it can be also re-expressed as the following form. Okay? And suppose that this will give you a value of theta. So according to the relationship here, we know that tangent theta will be this value. So the triangular will show you the tangent theta will be have 1 in this side and C in this side, and this side will be square root of 1 minus C square. Okay, so for the same value of theta, it can also be written as arcsine C. So this equation can be rewritten as okay, and then we use the C here to re-express the term on the left hand side. It can be written as Kn1A square root of 2 delta times C. According to the final expression here, let us define a very important parameter. We call it normalized frequency. The normalized frequency V is defined as Kn1A times square root of 2 delta. According to the expression you know that the capital V is in proportion to the inverse of lambda due to the K is 2 pi over lambda. So it is a normalized, it is a frequency. Besides, this expression include the cosine and the index of the co and the index difference. So it is the normalized parameter. So we call it normalized frequency. And from this equation, we know that this normalized frequency will equal to n pi over 2 plus a cosine C divided by C. Okay? Then we have the relationship between capital V normalized frequency and C here. So we can plot their relationship in this figure on the right hand side. So this figure shown here plots the relationship between C and the normalized frequency capital V. And for different value of M, it will plot it in the solid curve with different colors. And you can see that for this black curve, it represents guiding mode for M is 0. For this red curve, it stands for the guiding mode for M is 1. And this curve is M is 2. This curve is M is 3, as you can see in these figures, in these curves. Then, use this figure, I will show you several important properties of the waveguide. As I have said, for guided mode, the value of C should be between 0 and 1. As C is larger than 1, we will not have guided mode. So you can see the range along this axis is between 0 and 1. As C is larger than 1, we will have no guided mode. This means that for M0 mode, it will appear as the normalized frequency is 0. And for M1 mode, it will appear as the normalized frequency is at this value. What will be this value? As C is 1, we know that a cosine C will be 0, right? And the C will be 1. So the value of this point will be 1 times pi divided by 2. Okay, again, as C is 1, this term will be 0 and this term will be 1. So the value of this point corresponds to the normalized frequency is 2 times pi divided by 2. As a result, for M3 modes, you will have that it will appear as the normalized frequency is 3 times pi divided by 2. For M4 mode, it will appear as the normalized frequency is 4 times pi over 2. And this will be 5 times pi over 2. So these points represents the frequency as this mode start to appear on this waveguide. So we call this frequency VC, which means the cutoff frequency. Okay, so we can say that the M small will appear on this waveguide as the normalized frequency is larger than m times pi divided by 2. Okay, so for m0 mole, it will appear on this waveguide as the normalized frequency is larger than 1. As for the m1 mole, it will appear on this waveguide as the normalized frequency is half pi. For m2 mole, it will appear on this waveguide as the normalized frequency is larger than pi. So you can easily find out the cutoff frequency of each mole and know that as the normalized frequency is larger than the cutoff frequency, the mole will start to appear on this waveguide. So from these properties, you can easily to find out how many moles will be on this waveguide. For example, if you consider the normalized frequency is 4, you can plot a dashed line like this. And easily you will find out that this dashed line have 3 intersections with these small curves. As a result, this tells us that as the normalized frequency is 4, we will have 3 moles on this waveguide. These 3 moles are m0 mole, m1 mole, and m2 mole. Okay. Besides, you can see that as normalized frequency is 4, which is, I shall write it like this. V is 4 is smaller than 3 pi divided by 2 and larger than 2 pi divided by 2. So we can from this relationship know that we will have m0 mole, m1 mole, and m2 mole on this waveguide. Okay. So if the normalized frequency is smaller than m pi divided by 2, so there will be guided mole 0, 1, 2 until m-1 mole on this waveguide. So you can easily answer my question that if the normalized frequency is 15, how many moles on this waveguide? Okay, it will be the 15 will smaller than 10 times pi divided by 2. So there will be m0, m1, m2 until m is 9. Okay, so these moles will appear on this waveguide as the normalized frequency is 15. As a result, we say that at this condition, at this normalized frequency, there will be 10 moles on this waveguide. This is the one properties we can learn from this figure. Another property is that usually we like to have single mole in optical single mole waveguide in optical communication system. So let's see how we can have single mole. What I mean is, under which condition we will have single mole waveguide. To have single mole means that we only have m0 mole, and we don't want m1 mole to appear on this waveguide. As a result, before m1 appear on this waveguide, we will only have 1 mole, that is m0 mole. Okay, so the single mole condition will be the cutoff frequency of the m1 mole. So as the normalized frequency is smaller than the cutoff frequency of m1 mole, that is pi over 2. As the normalized frequency is smaller than half pi, we will have only guided mole on this waveguide. This means that we will have single mole waveguide. Okay? Since we have known the condition for the single mode waveguide, so how to realize such a single mode waveguide? We know that as the normalized frequency is reduced, we will have fewer guided modes on this waveguide. As we increase the value of the normalized frequency, we will have more guided modes on this waveguide. As for single mode, the normalized frequency should be kept under a smaller than half pi. By this expression for the normalized frequency, we can learn how to keep the normalized frequency smaller than half pi. First, you can reduce the value of the refractive index difference delta. To have single mode, waveguide, the first way is reduce the index difference between the core and the cladding. By reducing this value, we can have smaller normalized frequency to realize single mode. Another way to have smaller normalized frequency is to have smaller core size. If you can fabricate optical waveguide with smaller core size, there will be fewer modes on this waveguide. And under some condition, you will have only one mode on this waveguide. So one way to have single mode waveguide is to reduce the core size. The final way to have single mode waveguide is here. To reduce the value of k. How to reduce the value of k? We know that k is 2 pi over lambda, right? So this means that if you want to reduce k value, means that you can increase the operation wavelength lambda.